So actually, yesterday we have already mentioned a little bit about this page, so just skip it. So actually, if you try to explain how does the Schrodinger equation comes from, we need to make some assumption. The first one is to we assume the solution will be a plane wave. It's very strange. Originally, when you try to solve a problem, you try to write an equation governing the problem, and then you try to solve it. But in this case, you try to imagine, oh, this is the solution, and then you try to imagine what is the suitable equation, so that the solution will be this one. So it's the other way around. And the second one is the Broglie relation. The Broglie relations, which is actually P equals h bar k, and also E equals h bar omega, which is the momentum, and also the energy. So yesterday I already mentioned that the operator is just like something actually to operate on the wave function. It's just like you tell the robot to move forward for one step, maybe turn left for 90 degrees, something like that. So an operator is somehow like doing partial derivative to the function and multiply by something. So this is a claim. It's hard to explain why we will make this claim, but after we make this claim and derive the following equation, and everything looks fine. So here's the momentum operator. We hope this momentum operator p hat, okay, if the character with a hat on top, we'll call it an operator rather than a variable or value. So it's a momentum operator. We hope when we add this momentum operator to the wave function. So the wave function is this plane wave. We hope it output the momentum h bar k like this, h bar k phi xt. We hope it look like that. So when we try to observe this plane wave, we have exponential to I kx minus omega t. So we hope it to output something like k. So we may try to consider to take partial derivative with respect to x rather than t, because if we take partial derivative with respect to t, we will output minus I omega rather than ik. So when we take a partial derivative of x here, it will output ik. But at the end, we hope it to be h bar k. So we need to multiply it by h bar and then divide it by I, so that I and I cancel, and then the remaining term will become h bar k, which is what we expect. So we also multiply h bar over I here. So this is just a equation here, and then we will try to call this stuff the p hat. If we define the momentum operator to be the red term, this one, which is actually this one, and then we add it on the wave function or the plane wave, then it will output h bar k, which is the momentum. So when the momentum operator operates on the wave function, then it will output the momentum. If you have other operator, maybe the energy operator, which is called the Hamiltonian, and then you add on the wave function, it will output the energy, and so on. So we will call this h bar k the eigenvalue of p hat, and this is called the eigenstate of p hat. So this language comes from the linear algebra. So if you have ever learned the matrix, not the movie, the matrix is 矩阵嘛. So maybe you have a matrix like A is maybe 3 times 3 matrix. So when we try to, or maybe 2 times 2 is easier to write. Yeah, maybe you have a 2 times 2 matrix, and then you have a so usually when you try to calculate the matrix multiplication, maybe your AX is maybe 2, 1, 2, 3, maybe like this, and then you multiply by a vector, maybe 1, 2, then the answer will be 2 times 1 plus 2 times 1 plus 1 times 2, and then you have 2 times 1 plus 3 times 2. 2 times 1 plus 3 times 2. So this is the matrix multiplication. I think you have already learned it, right? No? Okay. So this is the matrix multiplication. So maybe let me finish this. So it's 4, 8. So it's somehow like you have a matrix. Maybe you write on the white dot. Maybe if we have a matrix, A is like this: A11, A12, A21, A22, and then B is another matrix: B11, B21, B12, B22. So if we have A times B, which will becomes this term multiplied by this term multiplied by this term, and then add together. So A11 plus B11 times B11 plus A12 times B21. And then for this term, which will be A11 times A12 plus A12 B. This one should be B, A12 times B22. And then for this one, A21, A22 times A11, A21. A21, B11 plus A22, B21. And then for this one, A21, A22, and then B12 plus B22. So you can see the rules here. So you take the first row and then take the first column, and then you have the inner product. And then the second row, the first column, and then we have this one. First row, second column, you have this one. Second row, second column, you have this one. So it's somehow like that. So matrix multiplication may be a bit complicated, but when you're given a matrix, there may be some vector will satisfy when you have a matrix multiplied by a vector. A vector is somehow like a one column matrix. It will satisfy something like this. It is a scalar multiplied by the original vector. And this is called the eigenvector. This is called the eigenvector. This is called the eigenvalue. 中文叫做特征向量跟特征值。不是所有的向量都会满足这个。对于一个给定的一个矩阵来说，它只有有限个向量，会满足这个特性。那它配对的那个特征值就叫做特征的那个值就叫做特征值。那它们一起叫的话，就叫做 eigenpair， 特征对或者所以说这个语言是从线性代数来的。So this is an momentum operator, and h bar k is called the eigenvalue of p hat. So it shares a similar topology. So you can regard an operator is somehow like a matrix, and then that wave function is somehow like a vector. So you have x here, you have exponential to something here, exponential to something here, and then you have this operator, and then it's somehow like a scalar multiplied by this one. So they share the similar topology. And then next we define the energy operator. So the energy operator, we call it the Hamiltonian. So we use h hat to represent the energy operator. We hope it will output h omega. So similarly, we hope this Hamiltonian acting on the wave function will output h bar omega. So we will try to consider, or we take the partial derivative with respect to the time. So it will output minus I omega. So finally, we hope it to be h bar omega. So we try to multiply it by I. So I squared will be minus 1, and then together with this will be positive 1. And then we additionally multiply by h bar. So that finally it becomes h bar omega. And then we will define this stuff to be the energy operator, the Hamiltonian. Yeah. So similar to the case for the momentum operator. So now we have the momentum operator. We also have the energy operator. And the next step is we can further define the kinetic energy operator. 那我们有动量，我们就自然会有那个动能嘛，kinetic energy operator. So in classical mechanics, we know that the kinetic energy should be 1/2 mv squared, or in quantum mechanics they prefer p squared over 2m, but actually they are the same, because you only multiply it by m and divide by m, and mv is p. So we have p squared over 2m. And in this case, we can imagine k hat will be 1 over 2m. 1 over 2m is a constant, so we can just put it there. And then we add the wave function by the momentum operator 2 times. We operate by 2 times, then you will have p squared. So we already have a p hat to be h over I partial x. So we make it 2 times. So finally we will have h bar squared here, and then I will be minus 1. So we have a minus sign. And then also we have 2m here. And then we have 2 partial derivative with respect to x. So we have the second partial derivative here. So this is the kinetic energy operator like this. So we have the kinetic energy. We have the total energy. So we can also assume it also satisfies the conservation of energy, 能量守恒. So in this case, we should have h hat should be equals to the kinetic energy. H hat is the total energy, k hat is the kinetic energy, and U is the potential energy. So this satisfies the conservation of energy. So if we add H on the phi and K plus U on the phi, they should be satisfied. U is the potential energy here. So the Schrodinger equation in 1D should be like this. And we just substitute h hat to be I h bar partial t, I h bar partial t. And then we also have a k hat. K hat is this one. K hat is this one, so that we put it here. And then U is the U depends on the environment. It's just like when we talk about the tunneling effect, we may have a potential tunneling effect. Maybe we have a wall in between. Maybe it's just a free variable or free function. So we just put U there. And in 3 dimensions, we can change this second partial derivative with respect to x to the Laplacian, similar to what we have learned in chapter 33, the wave equation. So this is just the derivative in the space, but in 3D. So, and we also change x to our vector. But we will not use that. So we try to solve this one. Actually, we can make some calculation, and then we'll come up this equation appear in the lecture slides. We only need to do some simple calculation. Actually, what we need to do is somehow like what we do in chapter 33. We assume the wave equation is separable. The wave function is separable. So it can be separate to be a function of x and another function of t. So we can substitute. So this is called the time-independent wave function. Actually, this one is not time-independent wave function yet. But if we try to derive the time-independent wave function or the time-independent Schrodinger equation, which you have seen on the lecture slides or the textbook, so you need to make this assumption, because you assume this does not change with respect to time. It is a stationary state. So the wave function does not. This part does not depend on time. This part does not depend on the space. So we substitute this one into here. So on the left side, we take the partial derivative with respect to time. So this is the constant. So we can factor it out. And then for this one, we take the second derivative with respect to x. So this is the constant. Time. So we have phi x here, and then phi t is isolate. So in this case, we can divide both sides by. So we can divide both sides by phi x, phi tt. Divide both sides by these two terms, and then this one go to here, and then we have IH bar there, and then on the right side a little bit more complicated. We have 1 over phi x, and then this term. And similarly, because on the left side is a function of time, on the left side is a function of time, on the right side is a function of x. And they are equal to each other, so they should be a constant. And this constant is actually the energy. You can check the dimension. They should be an energy. So we move further. So we make some simplification. This time equals to x. This part equal to E. This part equal to E. So we have two separable ODE. Actually, because this only related to time, so actually we can replace run to be D. This also can be replaced to be D. Can be D. Is the ordinary derivative. So solving the first order ODE is very simple, right? So we just make some substitution. So we can make it S equals EIH bar. Like this. Or actually, it will be like minus I E over H bar. So, which means that phi t should be this one multiplied by t and then take the exponential function. And similar for this one, S plus I E over H bar. This is that one. This will be the same. This will be the same. This will be the same. So for the t part, we have this one, and it looked a little bit different from before, but actually we know that E is actually H bar omega. E is H bar omega. So finally, we have a phi tt to be exponential to minus I omega t. We have the time part of the wave function. So for the second one, we have this one to be E. So this is a second order ODE. This is second order ODE. And it's not so difficult yet. So we slightly rearrange the term. We move this term to the right side and move this term to the right side. So this one become positive and this one become, it become like this, E minus U times phi x. And we can divide H bar square over 2m on both sides, and it become like this. And actually, you see this one on the lecture slides or on the textbook. So it's already skipped all the previous stage there, so that it tells you that the Schrodinger equation look like that. So this is actually the time-independent Schrodinger equation. So if you consider much more complicated situation, maybe the potential energy is a function of time, then you may not use this. You cannot make this assumption. Then it will become a time-dependent wave function, and they cannot be separable. But for simplicity, for some of the case, you already assume that all the situation doesn't change, and you can assume that the wave function is time independent. So you can make variables separable variables, and then you come up with this time independent Schrodinger equation. So at the very beginning, we assume we have this as the solution, the plane wave as the solution, and then we also make some assumption like the momentum operator, energy operator, and the conservation of energy, and then we come up with this one. So actually, this one is a linear ODE. I suppose you learned this in signal and system. You know what is linear. Linear means if phi1 and phi2 are the solution to this equation, which means that alpha phi1 plus beta phi2 should also be solutions to this Schrodinger equation. Alpha or beta are arbitrary constant, or even complex number. Yeah, so this is linear. So you can check this PDE is actually or this one is already this is PDE. Yeah, this is PDE. This PDE is actually linear. In this case, maybe we have different plane wave with different k, different omega. So we can add them together to become the new wave function. So if there are many different cases, how about for this case? So actually we can just use many different arbitrary constant to multiply different k. Maybe, yeah, I think let me see. Maybe this one should be k2. This should be k2. And in this case, k2. So in this case, we have different k, and then omega is a function of k. So different k, we have different omega. And in that case, we will have different coefficient for many case, continuous case. So this is called another phi k, and then we multiply with different plane wave with different k, and then we add all of them together. But there are infinitely many k, so that we need to use the integration. Use the integration. So in this case, we can just separate that. This one is a function of k, and then we have these parts. This is exponential to ik dk. So this looks very similar, right? This looks like a Fourier transform. But actually, maybe you learn this in signal and system. It's like xt exponential to minus j omega t dt, something like that. But yeah, different textbook have different definition. So it's actually like a Fourier transform. So when I talk about the Heisenberg uncertainty principle, I tell you that the k domain and the x domain is somehow like the Fourier transform pair. So this is in k domain. This is in x domain. So you can also assume that this is time independent, so that you can isolate this exponential to I omega t, and then you can just cancel that one. So you can see a clear picture like phi x is nothing but this phi k exponential to ikx dx. So it doesn't really matter whether we have a minus sign there, because it's just like you flip the axis. So it's nothing. It's not so important there. So it's just like the Fourier transform pair, and yeah. So that's it for this this one.